Okay, we're in the second year Stats and Mechanics textbook, and we're looking at exercise 6D. So chapter 6 is on projectiles and 6D is on projectile formulae. Okay, so we have, start getting a sketch. Okay, so we've got a projectile launched from a point on a horizontal plane with an initial speed of u meters per second at an angle of alpha. Moves freely under gravity until it strikes the plane, and first thing we're asked to look at is the flight time. Okay, so this particle is going to carry on up for a bit. Gravity is going to be slowing it down in the vertical direction, and then it's going to eventually bring it back down until it hits the plane. And they have said that the range of the projectile, so by that they mean how far it gets in the horizontal direction, is r. Okay. Right, so show the flight time of the particle is 2u sine alpha over g. Well, let's think about what is going to dictate the flight time of the particle. So that's obviously when it's going to end, and that is going to be when its vertical displacement is 0. Yeah, so it's going to hit its journey ends when it hits the plane. So that is when it's back to where it started in terms of its height, so in terms of its vertical displacement. So that'll be when its vertical displacement is 0. So there's going to be 2 points where its vertical displacement is 0 at the very start and when it hits the ground again. Okay, so we're looking vertically. So what else do I know? Well, let's take up as positive. So the initial, we'll use the purple, let's use a different color, right? So the initial vertical velocity, so that is opposite angle alpha. So that's going to be capital U sine alpha. So that's my initial vertical velocity. I know the vertical acceleration is going to be due to gravity, and if I'm taking up as positive, it will be minus g. And I'm after the flight time. And because t is the same whether I'm talking vertically or horizontally, I'll just call t. I don't need to use a subscript to say if it's vertical time or horizontal time. Okay, so what am I going to use for those? I'm going to use S is ut plus a half at squared. Okay, so S is 0, U is capital U sine alpha times t, and then plus a half times A, and A is minus g. So I'm just going to move that minus to the front there, and that's going to be minus a half g t squared. Okay, so I've got a quadratic in t, but it's not that bad because I can just take out a common factor of t. Yeah, so I've got t, didn't really need to do that. I've got a t in the first term and a t squared in the second term. So if I take out a common factor of t, that will leave me with u sine alpha for my first part of that answer, and then minus a half g t for my second part. Okay, so there's two solutions there. There's either t is 0, which we said it would be. So t is 0 is that point there. So when it first gets projected, its vertical displacement is 0. Or there's the solution in these brackets, which is u sine alpha minus a half gt is 0. So if I rearrange that to make t the subject, to avoid having negative coefficients, I'm just going to add the half gt over. So I'm going to multiply by 2 to cancel out the half, and then I'm going to divide by g, and I'm going to look back to the question and just double check. Brilliant, yep, we have got exactly what they wanted. So Just a brief conclusion as it was a proof. Okay, one down. So that was part A. What do we need to do for part B? Show that R is U squared times sine 2 alpha over G. Okay, so going back to our diagram, so R is the range. So we now know that it hits the ground. Well, we didn't. So even if we hadn't been able to answer part A, we were given in part A that it's hitting the ground at after 2u. So just copying that result there that we've just proved. Okay, so let's think horizontally now. So if I'm thinking horizontally, so horizontally, the initial velocity, different color. So the initial horizontal velocity, well, that's adjacent to the hypotenuse, to capital U. So that's going to be U cos alpha. So horizontally, my initial velocity is U cos alpha. The displacement horizontally we're calling R. We know that time is 2U sine alpha over G. And horizontally, because we ignore air resistance, the acceleration is 0. So I can use Suvat. I could use S is ut plus a half at squared. Made a bit of a mess of that. Let's write that again. So the horizontal acceleration is 0. So I can use Suvat. Or when I'm working horizontally, I can just say that displacement is velocity times time because that is constant. So, I mean, if I used S equal, get rid of that, try and get rid of that. There we go. Okay, right. So if I use the Suvat equation, S equals ut plus a half at squared, all that would happen is, because A is 0, that just ends up being 0. So it works if you use Suvat, but you don't need to. Okay, so my displacement, which we're calling R in the horizontal direction, is my velocity, which is constant, so U cos alpha, multiplied by time, so multiplied by 2U sine alpha over G. Okay, so let's think about tidying that up. So I'll bring the U, well, so I could bring the 2 out to the front, but actually if I look back at what I want, they don't have a coefficient of 2. They do have the U squared, so the U times the U does give me the U squared. Then I've got 2 cos alpha sine alpha, and that's all over G. And our double angle formulae do come up quite a lot in these questions. So as long as I recognise that is the double angle formulae for sine, I've got the result that they want. So 2 cos alpha sine alpha is sine 2 alpha, and that's all over G. And again, let's just show that we have finished. Okay, right, we're on a roll. Deduce that for a fixed U, the greatest possible range is when alpha is 45. Okay, so this isn't an exam question, so we're not given an indication of how many marks this would be worth, but it would only probably be a couple of marks. That tells us it should be relatively straightforward. So they're asking us, so let's just scroll down so you see the question. So the greatest possible range, so basically they're asking us, how can we maximize R? So, well, if we look, so it says for a fixed value of U. So we can't do anything with U. G is obviously fixed. G is 9.8. So it's the sine 2 alpha I'm looking at. So the maximum value of sine of any angle is 1. And this would occur, so this is when alpha equals 45 degrees because, sorry, I'm getting very messy, but because sine 90 is 1. Okay, so your clue is that questions like that are only worth a mark or two, so we're just sort of sticking a little bit of trig in there. So how can we maximise that? Well, they're saying that it's for a single fixed value of u. We can't do anything with g, so really it's the sine 2 alpha we're looking at. Maximum value of sine is 1, so that will happen when alpha is 45 degrees. Okay. Right, so given that r is 2u squared over 5g, find the two possible values of the angle of elevation at which the projectile could have launched. Right, okay. So I think we're really moving away from mechanics now, because so they've given us this new equation for r. So r is 2u squared over 5g. We've got this, and if we hadn't have got this, then they gave it to us in part B. So I think it's just going to be a case, of solving that. Okay, so find the two possible angles of elevation. So what can happen here? Well, they're both over g, so I can multiply through by g and cancel through by u squared. So what does that leave me with? So on the left-hand side, all I'm left with is 2/5. On the right-hand side, all I'm left with is sine 2 alpha. So actually, not a particularly horrible question to solve. So it's just not getting put off by all of these u squareds and fractions. So basically, all this is putting that equation for r equal to this equation they've given us for r, and then solving it to find the angles. So if I inverse sine 2/5, I get 2 alpha is 23. Let's go to 2 decimal places for now. So 23.58. They've mentioned two solutions. So alpha can be anything from 0 to 180. So if I want my second solution, I'm going to do 180 minus my principal value. So that will give me 156.42. So alpha, I'm just going to halve each of those. So that becomes 78.2 degrees to one significant figure. And 23.58 divided by 2 is 11.8 degrees. Okay, so really, like I said, just a solving, a relatively simple solving trig equation for part D. It's just disguised as a much nastier question. Let's just check those answers before we get too cocky. Okay, yeah, so they didn't mention, it makes sense to round to the nearest degree, because we were given the angles to nearest degree, but didn't specifically say that. And I didn't actually use G because we cancelled through, so I think I'd be okay to give answers to 3 significant figures, but 2 significant figures is fine as well.